Alright guys, today we're going to be looking at Craft. This is a software that comes out of the Onic lab. It was primarily spearheaded by Danila, who's now doing his PhD program in France. So Craft is chemical recommendation and analysis for future targets. What does this entail? Well, firstly, let's download the zip folder. I have it already installed. Then you're going to pull up your code editor because this is a Python notebook interface. So I have it downloaded somewhere here. I drag and drop the entire folder. Then we just want to look at the main Python notebook. So you can select your kernel, and if you don't have any familiarity with Python kernels, whatever, it's pretty simple. If you don't have any familiarity with Python notebooks or with environments, it's pretty simple. I mean, in the meantime, you could just follow the requirements here. If you're in terminal, you just open up your terminal on Mac or your PowerShell in Windows, and then you just copy and paste this over here, and that's pretty much it. Otherwise, you could get more. You could install Conda, and then you could do Conda activate environment, and whatever that environment would be called would have this requirement, and then Conda deactivate, however you want to do it. But today we're going to be looking at the Python notebook. So this folder path is pr2sifs. You could put in the entire directory. I'm working with the same exact folders that's in this, but I'm going to leave it to the following. So now all I'm going to do here is I'm going to hard code the path, and this is exactly what I want to see because I'm working with the same folder of CIF files. So it works through all of the CIFs that currently exist in your system, assuming that it's the same structure type, which is how you want to sort of work it out. Takes in all of the existing compounds, works with the same entry prototype, literally just reads it as is, and you can see that it's just a folder of CIF files that are the same structure type. So now, this is where it gets a little tricky. You'll have to designate particular sites for example, your R, your rare earth, M being your metal, your B metals, and X, maybe it's a P block element, however else it may be. So for this, this is really helpful because it assigns your sites. So for example, your rare earth elements are going to take up your 2A, 6H1, or 12K sites. With this particular structure type, your metals take up your 2C, and if you look at the 2C, you can see they're osmium, ruthenium, nickel. Your rare earths are in holmium, 2A, right? Yttrium, erbium, 6H1, 12K, and then your 6H2 is going to be your X. So in this case, it's aluminum, it's cadmium, whatever else it may be. So it's up to you to look at a particular structure type, read this out, and assign it accordingly, because this does have a big effect on how the PLSDA, PCA is ran. So merge them into a unified chemical formula per the group, and then it'll assign it all just like this. And you can see that the stoichiometric ratio does end up get filtered out later. And then what we do is we get weighted features based on the stoichiometry of the constituent elements within the compound. So back to our scheduled programming. I had to debug this. Now it should be all okay. So you can see we generate a number of different features all throughout for our entire composition, and now we could run our PLSDA with two components. We could see good separation here, good clustering, and then we'll continue, have our PC2 plots, we get the following, and now we could visualize the elements as they're generated. That's all fine and dandy, and then continue on, which is good. And now we could print recommendations. And again, all we have to do, we don't even have to swap out too much, but if you're going to be using different compositions, different structure types. Obviously, you're going to want to change your X, change your M. And what this says is we fix the metals for ruthenium, we fix the X elements that we assign for cadmium. So now we should be able to get a recommendation for our rare earth element. If you run that, you see we have 3 different recommendations. Recommendation 1 is a terbium, recommendation 2 is gadolinium, and the final recommendation is also gadolinium. And because of that, the next best candidates will be gadolinium and then samarium as well. You can see samarium's a 3rd here, the 2nd here, and the 2nd here. But we don't see a terbium in recommendation 2 or 3 at all. So that's sort of how that works. And then we update the data frame to add the candidate. Alright, now it gives you the candidate formulas, it adds it over right over here, gives you the CIF files, and now you can visualize where they lie within your actual composite set. You can see the gadolinium is right here, ruthenium, and then cadmium over here, so this is where that should lie. And the samarium, which is our secondary recommendation, lies over here. So obviously this all runs in a Python notebook. It's all very streamlined, very straightforward. Do a lot of visualization, different analyses, so on and so forth. And this just gives us a very simple way to generate recommendations without any inherent chemical knowledge. And again, our focus is the fixed site substitution here, and you know, again, exploring the PCA defined space, and so on and so forth. So again, we do expect to release a Craft 2. This Craft 1 was experimentally validated over in, I think, a paper published in JAX, if I remember correctly. So that was Jabrahimi et al. And so we actually made gadolinium 10, ruthenium, cadmium 3 for that particular structure type, and it's since been patented as a possible space shielding material, as well as a nuclear reactor material, due to the fact that it's pretty heavy on the gadolinium and the cadmium, and these two both have significant neutron absorbing qualities, so on and so forth. So if you're interested in the paper, feel free to read it, and we go in depth quite more on the software. So again, any questions, please feel free to reach out. Happy to help, and we hope you guys use Craft.